let's move ahead to our second speaker of the morning, David Jones from UC Santa Cruz. David has an invited talk using the Roman Space Telescope Supernova survey to unravel cosmic controversies. So David, if you could unmute yourself and share your screen, we could press on.
All right.
I'm Seppalainen. I'm going to run the timer. So if you want to pin me, you should find me. Leave my video open. So.
Thank you.
Yeah, if you don't, David, we'll remind you at the 5-minute mark. You'll be fine if you can't find it.
All right, I think it is pinned and everything. All right, can everybody see my slides?
Yeah, it looks great.
Awesome. Yeah, well, thank you so much for having me. It was so cool to see an overview of the project and yeah, all the pictures of the hardware and start. It's awesome to get even more excited about Roman, and I'm really looking forward to the rest of this conference, hearing everybody talk about the kind of diverse astrophysics, time domain astrophysics science cases that Roman will have. I'm really happy to start things off though with some summaries and what we're doing to prepare for one of the core surveys, the Supernova survey for understanding dark energy. And so on the supernova cosmology side, I think we're here because we want to understand what dark energy is. Dark energy is 70% of the energy density of the universe, and its nature is unknown. This figure on the right-hand side shows the dark energy density as a function of dark matter density. And it kind of shows how far we've come in the last 20 years to understand the 70% of the universe, with the open contour showing reset all 1998 and the Pantheon sample in red. And I know there's going to be a slight revision to these contours as well very shortly. I think the new Pantheon Plus sample led by Dylan Brout will be on the archive tonight. So definitely look forward to that. So in spite of the fact that we've made a ton of progress over the last 20 years, we know that dark energy is consistent with cosmological constant to plus or minus 4% or so, but we really don't have good constraints at all on the possible redshift dependence of dark energy. You can see in this figure on the right-hand side, if you just expand the parameterization of your dark energy model at all to include some kind of dependence on redshift or scale factor, the uncertainties just balloon massively. And so this is where Roman is really, really going to help us. And it kind of shows that our understanding of this huge component of the universe is really not as good as we think it is. And add to that, I'll talk about the Hubble constant momentarily, but some of this potential evidence for tension in lambda CDM parameters like the Hubble constant and possibly the growth of structure parameter sigma 8. To me, it just emphasizes that our understanding of our cosmological model is not a solved problem yet. And so Roman will be tackling this with multiple surveys, but one of them is, of course, type 1a supernovae, which are a standardizable candle that can measure distances up to 5% accuracy. This kind of classic plot on the right-hand side shows that if you take into account the fact that intrinsically more luminous supernovae have broader light curve shapes and bluer colors, you can standardize supernovae to get this bottom plot of brightness as a function of time. So current surveys are constraining dark energy properties with about 2,000 of these type 1a supernovae. And of course, type 1a supernovae were important for first discovering dark energy and measuring the Hubble constant tension. So when I talk about the Hubble constant tension, I'm talking about the difference between the value of the Hubble constant predicted from the cosmic microwave background versus the one directly measured today. So from the CMB, taking cosmic microwave background measurements at the sound horizon, including our cosmic matter and energy budget, the laws of general relativity, and of course, evolving those predictions over 13 billion years of cosmic time, which importantly, Roman data cover most of these 13 billion years. That leads you to a prediction for the value of the Hubble constant in the local universe of, from Planck, 67.4 plus or minus 0.5. So if we go out and measure the Hubble constant directly, and those measurements disagree, that means our knowledge of cosmology is off somehow. One of these ingredients isn't what we think it is, or there's the systematic uncertainty somewhere. So I'll get back to Roman momentarily, but I want to just explain where these local measurements come from. There are a number of ways of constraining the Hubble constant in the local universe. The kind of traditional way is first using geometric distances to calibrate the luminosity of Cepheid variable stars. So that's starting on the left-hand side here. And then second, using Cepheids in nearby galaxies to calibrate the luminosity of type 1a supernovae. And then last, on the right-hand side, observing type 1a supernovae in the Hubble flow to measure the distance versus redshift relation and constrain the Hubble constant. And in fact, when we look at CMB measurements versus local measurements, so blue versus red, we see a difference. There's the difference between the two most precise measurements in this plot, Planck et al. 2018 and Rees et al. 2021, has recently surpassed 5 sigma significance. There are multiple ways, of course, of measuring these things. Tip of the red giant branch measurements have recently been coming in more in the 70 to 72 range for H0. Holy cow and megamaser measurements that strongly lens quasars and using megamasers as a standard candle are coming in more at 73 to 74. And if this discrepancy holds up, these are kind of the simpler lambda CDM model extensions or non-lambda CDM model extensions that one might expect could explain this discrepancy, starting from the top, changes in the dark energy equation of state or the evolution of the dark energy equation of state, a number of effective neutrino species, curvature, dark matter radiation interaction. And of course, there are lots of other potential models to explain this discrepancy, such as early dark energy, acoustic dark energy, self-interacting neutrinos that I won't get into too much today. So could this be due to systematic uncertainties? Do we really understand our cosmological model after all? Well, I just wanted to talk about a couple things that I've been involved in recently in terms of seeing if this discrepancy is robust. The first of these things is trading out the optical type 1a supernova distances for near-infrared type 1a distances, which of course Roman will also provide a ton of extremely well-calibrated near-infrared supernova distances. This was first done, I think, by Dewan et al. 2018, and we recently did this again with a single photometric system from the Cepheid calibrators to the Hubble flow. And this was put on the archive a couple of weeks ago, and we saw that the Hubble constant stayed relatively high at 75 plus or minus 2.6 kilometers per second per megaparsec. There are some other things that people worry about with these measurements is Cepheid crowding. As you observe Cepheid galaxies farther and farther away, there's more blending between Cepheids and other stars. So what we did to address this is we made the crowding problem much harder on ourselves, and we observed Cepheid galaxies at about 70 megaparsec, which I think is about twice the distance of the farthest galaxies in the previous Rees et al. 2016 Shoes paper. And we saw that those Cepheid distances were consistent even at about 70 megaparsec. Whereas if crowding was a significant problem, you would expect it to become worse the farther out the higher distances you go to, and you would not see those galaxies agree with the Cepheid versus type 1a supernova distance trend. And then all of these faraway galaxies as well. This is an HST program that was in cycle 28. Unfortunately, it's not quite finished yet, but should be around next fall. We have 3 more galaxies coming at about 70 megaparsec. That enables us to entirely replace type 1a supernovae in the distance ladder method as another systematic check. And there will be some early work on this from Darcy Kenworthy that'll be coming out soon with these first 2 beautiful galaxies shown in the bottom here. So there are a lot more systematic tests in the recent Shoes analysis from Rees et al. 2021. I would say there's no clear physics or systematic error solution to the tension, which brings me back to Roman. So the Roman Space Telescope will really make a generation-defining measurement of dark energy with more than 10,000 type 1a supernovae. It's tasked with improving our knowledge of dark energy by a factor of 10, as it's parameterized by the dark energy figure of merit, and it will really rule out late universe solutions to the Hubble constant tension. And just how amazing these data will be, I think, is really illustrated in this right-hand panel from the Duray et al. 2019 Astro 2020 white paper that shows the stars in gold show the supernova distances currently as a function of redshift, and then the gold lines show the supernova distances that we'll expect from Roman. So this is really an order of magnitude improvement kind of across the board from redshift 0.5 all the way to 2.5. And this really unlocks Redshift's wavelength systematic uncertainty floors that were previously unreachable for type 1a supernova distances. I'll note quickly on the comparison to the Galaxy Redshift survey, there are more correlations between the supernova bins. I'm not trying to make a direct comparison to Galaxy surveys necessarily here. I just really like this plot. And I want to point out that Phil Macias will give a talk before very long, I think in the 10 o'clock session with more details of the supernova survey. I just want to also show some of the beautiful light curves from redshift 0.5 to redshift 2 that we're going to be able to find from Roman and measure fantastic distances. So there's this really nice paper from Ben Rose on the archive that presents a Roman supernova reference survey. And it presents a survey split between wide and deep field components that will discover more than 12,000 type 1a supernovae. And I'm really interested for the next few years on not only what Roman will tell us about the universe, but how we'll prepare for the Roman Space Telescope and enable all of this fantastic science. So from Ben's paper, two things to notice is, first of all, there will be more than 1,000 supernovae observed in the rest frame near infrared at these redshifts of less than 1 or so. There are also very few supernovae at redshift less than 0.1, which of course is where dark energy is the strongest. So this suggests that we need to really understand how to use type 1a supernova distances in the near infrared. And we need a low redshift sample of supernovae that will match the exquisite calibration of Roman at higher redshifts. On the systematic uncertainty side, this is a quick rundown of important systematic uncertainties in supernova cosmology, both the systematic uncertainty budget that's coming out tonight from Dylan Brout's paper and a paper with Pan-Star Supernovae that I led a couple of years ago. Particularly, Roman will have fantastic calibration, but we need to make sure the low redshift samples also have fantastic calibration. Supernova modeling, we need to make sure we understand selection effects, the relationship of supernovae to their host galaxies, redshift evolution in supernova standardization things, and Milky Way extinction. Of course, the fact that Roman has all of this data in the observer frame near infrared means that this Milky Way extinction component of our systematic error budget will just nicely diminish itself. So I wanted to start off by talking about how we use supernovae in the near infrared and what we can get out of those data, and then move on to talk a little bit about the low redshift samples. So in the last year, I worked on building the SALT-3 model with Darcy Kenworthy. This plot on the right-hand side shows the number of SALT-3 observations divided by the number of observations we'd expect to be usable with Roman from the previous kind of standard state-of-the-art supernova distance measurement method. And what we found is that by extending the model just a little bit to the rest frame Z band, we got 20% more usable observations from the nominal Roman supernova survey. So we're still finding ways to get the most out of these data, and it's not over yet. And it's always really exciting when you have a multi-billion-dollar mission and you can get 20% more out of your supernova data. And so we're working on doing even better with this process. On the right-hand side, this shows how supernova distances improve as you get more near infrared data. And then the main plot here, this is from Justin Perel, and he's going to talk about this more, just shows the equivalent increase in your sample size as you go to lower redshift with Roman, and you get additional near infrared data. And even at redshift 0.5, 0.6, this is a significant improvement in the scatter of our samples. The real challenge with using near infrared supernova data is, of course, making sure we have the near infrared data ahead of time to learn how to standardize supernovae in the infrared, get inferences about dust and supernova physics from those data as well. Of course, the Carnegie Supernova Project has been doing a ton of work on this. I think Eric Chow will probably talk about this some. But we've also been working to assemble hundreds of new, well-calibrated near-infrared light curves from UCURT. This is work that I'm doing with Dan Skolnick, Eric Peterson at Duke, collaborating with David Rubin as well. And these are some of our early data here that we've collected over the last couple of years. So I'm really excited about this sample and just having a really well-calibrated near-infrared sample, both to anchor the Roman data at low redshift and also understand how to standardize supernovae the best possible way in the near-infrared. And then simultaneously, I've been working on things with collaborators to measure supernova distances at higher redshift. And so this is a recent measurement of the dark energy equation of state that really for the first time measured near infrared supernova distances in the rest frame at higher redshift, thanks to a lot of investment of HST time. So we're still learning a lot about how to use the near infrared and building up new low redshift near infrared samples. We're also working really hard to build up new low redshift samples in the optical. And I kind of motivate some of the need to build up these large optical low redshift samples because we have to worry about differences in supernova properties between low redshift and the amazing sample that Roman will come up with. And so what I'm really talking about here is the fact that supernova distance measurements appear to change depending on the masses of their host galaxies. So this figure just shows the Hubble residual as a function of host galaxy mass. And there's a step between supernova distances derived from supernovae and low mass host galaxies versus higher mass of about 0.06 magnitudes. The reason for this is unclear. It could involve changing progenitor metallicities, different supernova explosion mechanisms, dust laws, and it results in systematic uncertainties when low versus higher redshift host galaxies have different demographics. Of course, we really have to worry about this for Roman when we go out to redshift 2, and host galaxies themselves are evolving significantly. And so particularly though, for the kind of legacy low redshift sample collected from 1990 to 2010, these were surveys that primarily targeted bright pre-selected galaxies to find supernovae, and the result is kind of this plot on the right-hand side that shows the fraction of supernovae as a function of their host galaxy mass and host galaxy star formation rate. In blue, this is a Cepheid calibrator sample for measuring H0. In gold is this kind of legacy low-Z sample, and in brown is a high redshift sample. And so there are significant differences across these samples. On the Hubble constant side, we've now in the recent CHOOSE paper selected our Hubble flow sample in a much more uniform way compared to the Cepheid calibrator sample. So the difference between this kind of blue histogram and the orange curve has gone away. But comparing low redshift to higher redshift, there's significant differences in these properties. And some of those are due not just to the evolution of galaxies with cosmic time, but due to selection effects. And also, we certainly can't match the Roman excellent Roman calibration with calibrations that were off by 3% or so, as was seen in this Skolnick et al. 2015 paper. So we've been working, I can't believe it's been 7 years, I think, but we've really been working to rebuild the low redshift supernova sample for Rubin and Roman. That started off with the Foundation Supernova survey. This has observed about 350 redshift less than 0.1 type 1a supernovae on the Pan-STARRS telescope. So these are supernovae with GRIZ light curves, with millimag level photometric calibration, a really well-tested reduction and analysis pipeline that was also used for the high redshift samples from Pan-STARRS. some Cepheid calibrators, and we removed some of these previous selection effects by following supernovae from untargeted surveys. And so this figure on the right-hand side shows a Pan-STARRS Hubble diagram all the way from redshift 0.01 to about 0.7. We have a number of publications on dark energy and host galaxies and supernova velocities, and these data have been used in lots of other cool studies, like the recent Pantheon Plus dark energy measurement that will come out tonight, growth of structure measurements, and lots of other cool things. And we've expanded this a lot further recently by turning the supernova follow-up survey into a supernova discovery survey with the Young Supernova experiment. We're using 7% of the time on Pan-STARRS 1 and shortly 7% of the time on Pan-STARRS 2. Actually now Pan-STARRS 1 is being serviced, so we're now working on, we're using Pan-STARRS 2 data, and once they get a boom lift up to the summit of Haleakala, then we'll be doubling our survey area. So this is following 1,500 square degrees of sky with a 3-day cadence, overlapping with transient surveys like the Zwicky Transient Facility or ATLAS, to just have really exquisite transient light curves, and also do great cosmology. And this is just an image of our survey fields on the right-hand side here. And I have to, of course, give credit to Matt Siebert for our logo in the upper left, which spells YSE out on a Pan-STARRS CCD.
Hey, David, you have about 4 minutes, a little more than 4 minutes left.
Great, thank you. So this is all extremely preliminary, but from 1990 to 2010, there were about 400 supernovae discovered at a redshift of less than 0.2. Then from 2015 to 2018, there were another couple hundred supernovae that have been published to date, probably another 100 cosmologically super useful supernovae that we still need to publish. And then in the Young Supernova experiment, compared to this 1990 to 2010 period, we're discovering about a decade's worth of supernovae for the Hubble diagram per year. And so we now need to get good redshifts for all of these, which I think explains most of the scatter here on this Hubble diagram. But all of these are samples that can match, particularly these newer samples can match the really exquisite calibration of the Roman Space Telescope at high redshift. There are also new surveys coming from DECAM, and Rubin will help as well, though the cadence isn't quite as good as what we're building with Pan-STARRS. I want to mention a couple other things that we're working really hard on to get the most out of Roman, particularly given some upcoming talks. We, of course, need to build sophisticated simulation tools, both at the pixel level, the catalog level, and spectroscopic simulations. I want to highlight this work from Justin Perel that simulates a flexible SED model for type 1a supernovae that basically makes it so we don't have to bake in a lot of assumptions about how supernovae behave or their physics into our Roman simulations of type 1a supernovae. We can really use flexible models and explore possible systematics and see how they impact the survey design. And so this kind of shows the steps all the way from a baseline SED model to perturbations, to the spectrum, to realistic noise, to Roman simulations. Photometric classification is also really important. Helen will give a talk on this as well, since we won't be able to get spectra for every single Roman supernova. And so learning how to use photometrically classified data, of course, a lot of you care about transient astrophysics as well, and photometric classification will be incredibly important for that also. And so last but not least, we're excited not only to understand the 70% of the universe made up of dark energy, but Roman is going to help us tackle some kind of decades-old questions in the type 1a supernova community, like what is the role of dust in supernova distance measurements? What are the physics behind how type 1a supernova Hubble residuals depend on their host galaxies? And how do these things evolve with redshift? How can we control for them in cosmological analyses? So with that, I'll end and just say that I'm really excited for the new constraints on our cosmological model from the Roman Space Telescope and understanding some of these persistent mysteries in type 1a supernova physics and progenitor studies. And there will be a lot more talks today. I apologize if I forgot everyone, but please look forward to some of these more in-depth discussions of the Roman survey. Thanks.
Thank you very much, David. That was a great talk. I just wanted to reiterate something that you said at the end, which is that people shouldn't forget that this session, we have the 3 invited talks in this session. They're going to get into David and Aparna next. They're going to get into the discussion of the Roman surveys. But there's many more talks coming up today and also tomorrow that go into a lot more detail about what we're thinking of might be the best ways to carry on these surveys. And as Julie mentioned, you know, we're still looking for a lot of input from the community on how to optimize all of these surveys that we're going to be talking about this week. So it's really an exciting time, and stay tuned for those. So do we have any questions for David? Please put them in the chat or the thread. There's if you look in session 1, there's threads for each speaker. You can put your questions in there. We'll take another look. Let's take a little pause here. And also want to remind the speakers, please go back to those Slack threads at different times during the conference, because people will put questions, and it's a good place to have a chat. I see there's already something from Julie from before in her thread. So don't forget to do that. You don't have to put the questions in right now. I don't see any in the chat right now for David. Let me check over at the thread. Nothing right now. David, I had a quick question. Maybe this will come up later. You know, now we reached with Rowan beyond 2 microns. So I imagine there's lots of discussions in the team and in the prep teams doing the prep for thinking about using the redder filters. Is that something that will significantly help a lot of the things that you were talking about, perhaps especially the latter ones about the controversy about the dusty galaxies or something?
Yeah, I personally feel that any way that we can get more near-infrared data, that's a really good use of time. It's one of the things that makes Roman particularly unique. Of course, it's a balance of sensitivity versus wavelength range, of course. But yeah, I mean, you know, extending beyond 2 microns, really what I think of that as doing is extending the redshift range at which we can use near infrared data and get better constraints on the supernova color and constrain dust evolution. Yeah.
Yeah, thanks. I took a little session chair prerogative there for asking out loud. Okay, I don't see anything. There is one. Okay, something just appeared in the chat. Let's just do that. I think, let's see what the time. Yeah, we have a little bit of time left. So there's a question. What's the current understanding of theoretical models on Supernova 1A?
Yeah, type 1As are definitely, especially on the cosmology side, they're very much an empirical tool. And I'm probably actually not the best person to answer this question in terms of type 1A physics. There's been, you know, on the observational side, there's been some really cool progress in terms of finding supernovae with early blue bumps and just kind of opening this first couple days of explosion window for type 1A supernovae. Of course, that's debated as to whether that implies a single degenerate progenitor scenario. And there's also been some really interesting stuff in terms of looking at how much supernova distances are affected by things like dust. And of course, that will have implications for how models reproduce the observed behavior of supernovae as well. So I think though I'm mostly going to defer and kick things over to talks like Eric Shao that's like really learning about type 1A supernova physics using the near infrared data and nucleosynthesis and things like that. But there's no doubt that any progress on theory will inform how good our cosmology constraints can be and how much we worry about particularly unknown unknowns when we think about whether supernova metallicity makes luminosities evolve at redshift 2.
Great, thanks, David. And yeah, I just want to remind, we're going to have a number of great talks on the supernova and the supernova survey, including use of the prism coming up in the next session. So please stay tuned for those. Okay, I don't see another question, but remember, you're not missing your opportunity. Just pop them in the thread, and I'm sure David will.
There is a question.
Or there's a question. Okay.
Slack.
Where? Oh, there is something in there. I'm sorry. My apologies. Thanks, Seppo. How robust are dark energy measurements to a single or double degenerate explosion mechanism or a mix?
Yeah, because it kind of follows up on the theoretical question. You know, because supernovae are used in such an empirical way, I think constraints are very robust. It's kind of unclear how much single versus double degenerate properties could affect supernova distances, but basically what we need to look for is how the standardization of supernovae changes. So how the color law evolves with redshift, or how the stretch correlation between supernova stretch and luminosity evolves. And you know, the only thing that we can never really guard against is if supernova luminosity was to evolve in some way that was totally uncorrelated with their stretch or color, and that's unlikely to happen. So there are lots of empirical games we can play, right, to match out host galaxy properties or match stellar ages from the low redshift to high redshift sample. We're not currently too worried about this, but I would say it's something that we will very much keep our eye on in terms of systematic tests that make sure we're comparing low redshift to high redshift supernova samples in a homogeneous way.
All right, thanks, David. Let's move on.